All right. Hi, everybody. Welcome to today's topical meeting, where Xiaocong is going to be telling us about some of the initial studies that she and some others have been doing with ACTS tracking with GPUs. So Xiaocong, why don't you go ahead?
Okay, hello everyone. So I'm going to give you a talk to show you some studies has been going on to explore how to use the GPU for accelerated tracking within the ACTS group. Okay, so the motivation behind this is that, as you know, we are going, the tracking is really time consuming, and this is particularly the case for future detectors, such as the high luminosity LGC, where we could expect up to 6K particles per event. And this also means the CPU consumptions will much increase with this high combinatorics. So this is also the motivation that we are going to have some new detectors, such as the ITK upgrade project at Atlas, and also the software optimizations, and even to write new tracking software to gain some performance and to not compromise the physics performance. But still, we might also want to explore some hardware as well to increase more performance gain. And considering that we have a lot of modern hardware, high performance hardware architecture on the market, such as the multi-core CPU with vector processing units, which can be used to support the Cindy instruction, and also the GPU with thousands of cores, even though they are little simplified cores. And also the little power consuming FPGA with some sort of tracking pattern for the track finding. Okay, next slide. So some recap of the ACTS project. And as said in many different places, the goal of ACTS, the first and also foremost is to prepare a detector independent tracking toolkit for future detector, such as the Atlas detector at high luminosity LGC. And it's written based on the Atlas tracking software, which is well tested. And our side goal of the ACTS project is also to provide the testbed for the tracking R&D. So currently, two explored directions includes the innovative fast tracking techniques, and this is usually based on the machine learning techniques. And there are various projects going on in this direction, such as the similarity hashing and learning, and also the GNN project for track finding, and also the ambiguity solver with the machine learning techniques. But still, as said, we can also explore the hardware since it's usually with multi-core and GPU, which can be used for the parallelization as well. So this is exactly the direction within this R&D project. So as you can see here, we have different types of meetings going on under the ACTS project. And there are some of them at the ACTS parallelization discussion, which happens usually once or twice per month, and which is even getting more recently. Actually, this R&D lines of ACTS is motivated by design of ACTS. For example, we have quite a complete set of tracking tools for the track parameter propagation and track finding and track fitting, and which usually have highly modular design. And also there are a lot of tests and examples which are very easy to run to test the implementation. And also there are a lot of plugins for different geometry description and IO and runtime API. And also the ACTS has the design to support the contextual condition data, and also very strict test for to ensure the concurrency of the code. So all of this motivates these R&D lines. And so in this talk, I'm going to focus on the parallelization studies going on within STS group. Okay, next slide. Yeah, so as said, we have different types of hardware, and this can be used for different purposes. So first is the multi-threaded event processing, and this is done in ACTS with the Intel TBV library to support the multi-threaded event processing. So as you can see here, we have this for loop, and which is used within this TBV library, parallel 4, so they can be run concurrently with also the different contextual condition data. As said, this is supported by this algorithm context, and they are event dependent. So as you can see here, this includes the geometry and calibration and the magnetic field condition data. But still, you can also run this using just one thread. And all of this is supported in the test framework of ACTS. But still, we also have explored using the multiple threads to speed up the intro event execution, such as the track fitting using the TBV library, which is used on top of the multi-thread event processing. So as you can see here from these plots, so this is the speed up gained using the multiple threads for the track fitting in ACTS on a given machine. As you can see, we have quite good speed up, but also we can see the reduced memory footprint as well, as you can see from this plot. So we have two loops of parallelization here. The first loop is for the event processing, and the second loop is for the track fitting. So if we use more threads for the fitting, we can see the reduced memory footprint. Okay, and since May of this year, we also started to implement some plugin to support the heterogeneous computing. So as you can see, we have already the CUDA plugin in ACTS repository. And this is motivated by the work to use the GPU for the ACTS seed finding. And this is actually the first contribution is from outside of CERN. And also, as you can see here, we are going to have the SQL plugin very soon. So we are going to have a discussion this Friday to discuss about this. So this is just to say that we have different types of plugin to support the different API. And as said, the first explored target offloaded to GPU is the ACTS seed finder, and because it's quite simple and the data structure is quite simple, and we have many we have good data node for the GPU with the seed finder, and the ACTS seed finder is taken from the Atlas. We have the very usually use the concept of the doublet search and the triplet search. And now with this CUDA and also the SQL plugin in the future, we have this put into the GPU kernel. So for example, the search of the doublet and triplet, and also some additional coordinate transform needed for the triplet search. As you can see here in this plot, we have even two versions for this. And this is because we are still running some validation tests. So we have different versions to cross-check the results. And here is some plot show the speed up we have gained with the seed finder on GPU. So so this is the time with the GPU and also just the CPU. So you can see the difference. We have the GPU for the seed finder. And then this is the speed up taken from this plot. So we have a factor roughly 17 at with with 100 K space points, which is the high velocity LTC tracking environment. So, so currently we are going to test some results with some realistic detector configurations and also the true sample selection to validate if this is really the case. And the second work that has been explored to use the GPU is the ACTS track propagator. And then based on this, we also explored the common feature, since the common feature is just part of the propagator, actually. And so first is the propagator design. As you can see here, the propagator is basically concerning the task how to transport the starting parameter step by step. And then we can do something on the surface with some measurements there. And so the ACTS propagator has a very highly tempered design templated on both the stepper and the navigator. So the stepper, we have different B field, and from the navigator, we can have different tracking geometry. And between those surfaces, as you see here, this is the job of the this is the job of the ACTS stepper, so which transport the track parameter step by step, including also the covariance of the track parameter. And then when we reach this surface, we can consider the material effects and also run the common filtering to update the track parameter based on the measurements. So if we don't have this material interactor and the common actor as part of the propagator, we can just run this pure stepper to update the track parameter. But also, as said, we can have the common actor, and then that will be the common feature. Okay, so first, if we look at this propagator timing performance on CPU, so this is some test performed by Andy quite a long time ago. And so we have various types of plots here. So first is with different stepper in ACTS. So we have 3 types of steppers here. The eigenstepper is the primary stepper in ACTS, and the Atlas stepper is just the Atlas stepper taken from Atlas. And then this is the straight line stepper. So the first plot is showing the number of steps per track. And then this plot is showing the time per track, the propagation time per track. And then this is the number of the time per steps. So we are going to just focus on this plot here, which is the propagation time per track. As you can see here, roughly we have 0.1 milliseconds per track for the eigenstepper. And so this is actually already very fast. And then I think at least on the optimization within one track might be very difficult. So instead, we are going to focus on the parallelization for the many tracks. That's the job we are going to do with the GPU. Okay, so before that, we also have looked at the common feature as well. As said, common feature is quite closely associated with the propagator. So the common feature performance takes a little bit longer time because we have the common filtering, but still the timing scale is quite similar. We have like 50 milliseconds like this per track. So for the next few slides, I'm going to show how could we use multiple threads to parallelize the many tracks with the GPU. Since the the intro track optimization might be very difficult. So we have this first try to look at the propagation on the GPU. So this is the propagation kernel we have used so far. So one kernel will be responsible for one propagation with the starting parameter and also the propagation options. And then you can take the propagation results from the GPU. And also, if we are using the Atlas B field, for example, we have to also consider how to pass the B field to the GPU as well. And this is not very easy, but still we have figured out how to handle this. And then, okay, so this is for comparison. This is on the propagator on the CPU. It is very similar. It's just that we have to use the propagation results as a parameter on GPU. And similarly, we also tried to put the common feature fit onto the as a feature kernel and put it on GPU. And so the one fit will take the starting parameter and also the input measurements, which is some source links, as you see here, and some options. And then we also have to give it the surface. So this is just some test with 10 surface. And then, as said, we have to define the fit results and then let the fit performed on GPU and take the results back from the GPU. All right, so this is the test setup for the ACTS common feature on GPU. So we have just the 10 plane surface here, which is the place where you see some green dots here. So the plane surface are placed perpendicular to the x-axis, and the B field is currently using the constant B field, which is 2 Tesla in the z direction. So you can see some curve of the tracks here. All right, so the performance of both the propagator and the common feature. So this is some plot we have quite a long time ago. We first just made the propagator running on GPU. So this is the performance we made at that time. And then, so until recently, we barely made the common feature running on GPU as well. And this is the performance of the common feature. And the results are tested on a different machine. But for both of these plots, the gold line is the results on the GPU, and other lines are on the CPU with some OpenMP parallelization or without some OpenMP parallelization. Sorry. But if you look at these plots, and the x-axis is the number of tracks. And if we just look at the 10K tracks, which is roughly the tracking scenario we're going to have at the high university, as you see, we don't see any overfill speed up compared to the CPU results with OpenMP parallelization, but still we can see that we can see the speed up compared to the CPU results without any OpenMP parallelization. And this is not so surprising because we are really not taking advantage of the GPU for one track. We just made the one track fitting or one track propagation running on GPU, but beyond that, we are not doing anything more specific to the GPU yet. So this brings me to this page. So we are currently doing some optimizations on the GPU implementation. So for example, we noticed that the registers, the GPU registers are really under pressure if we just use one thread per track, because we have a lot of very dense matrix operations for the track parameter propagation and also the common filtering. And And if we are really going to take advantage of the GPU, we might want to use more threads for this. So as you can see in this screenshot, this is one example. This is the loop of the propagation. We have different steps, and then for this step in one loop, we have this track parameter updated here, and then we are thinking to use like 64 threads for this. And we are using 64 because the maximum matrix dimension is 8. Sorry, this should be 8. It's 8 in ACTS. So we are going to use 64 threads for one track parameter propagation here. We can also use this in this common feature, which is on the action here, which is actually the common feature takes place. But this is just some idea, so it's still to be explored if this can work. And also, we also noticed that a lot of source code on the CPU is not very optimized in terms of like the memory usage. So we are also going to need to minimize the memory usage, for example, on the CPU as well, to really achieve some performance with the GPU. All right. So currently, we are just talking about the very simple implementation of the common filter concept on GPU. We are not talking about the geometry yet, because we just test the performance with some simple plane surface. But in the real case, we have to handle a much more complicated tracking geometry. And in ACTS, the surface is the key component. And this is included in almost every tracking EDM, such as the measurement and also the track parameter. And so we have to handle this very carefully. And the navigation with in the traditional way is considered not realistic, because we have a lot of different types of service in ACTS to be used for different detectors. So we have those virtual methods for those services, and unfortunately, this is not so easy on GPU because the GPU kernel cannot handle the virtual methods. And also, since we have different service, we might have a lot of branching points during the geometry navigation to say if this layer or volume or surface is reached. So a lot of branching points will come with this traditional geometry navigation. But very fortunate that we have some way to handle this on GPU. So in ACTS, all of those surfaces have some interface to get some type of polygonal representation, such as the triangular mesh of the surface. So this means that all of those surfaces will have the similar representation. And then, so with this, we can have the parallel navigation of all of the surface simultaneously. And this is exactly what GPU likes. Okay, so this is the interface of the surface. So from this, I said we can have the triangular mesh of all of the surface, and this will fastly speed up the navigation with this representation, benefiting from the GPU. And this slide is just one example of the track element detector represented by the triangular mesh. So as you can see here, all of those surfaces here is just some triangular. So the next plan with this work is that we are going to use this in this common filter navigation, and then if to also optimize the common filter itself. All right, the summary. And as you see that we have very active RG9 to explore the high performance computing architecture within the STS community to see if we can have some accelerated tracking achieved taking advantage of the GPU hardware. So far, we have already seen some good speed up with the GPU for the seed finder. But it's just that we have to do more work to validate the results with different setup of the test and also different detectors. Another work has been going on is to use the GPU for the STS common filter as well, but this is more difficult because it has all of those different data structures, including the track parameter, propagator, and the stepper, and also the track parameter and the geometry surface. So it can take much more time for this really running and has some speed up. So currently, we are thinking to explore the speed up by using multiple threads per track for those places that dense matrix operation is involved. And also, we are going to have our GPU dedicated geometry navigator for this common feature to make it really a common feature for different geometry. But some observations we have so far about the common feature on GPU is that this common feature still has some limitations because we have very limited parallelization workloads for the track fitting. For example, we have only 10K tracks, and also the matrix dimension is just 8. So it's not very easy to have a lot of parallelizable workload. And what's worse is that the workload is very unbalanced through the detector because we have different number of hits on different tracks in different place of the detector. So we have to consider all of this. And also, even we consider this, we have some penalties with this common field on GPU because the GPU is just the GPU, it's not the CPU. So we can lose some flexibility with the GPU, such as the different service and also that we can't handle the different different numbers of hits on track very easily. And all of this is very careful consideration. But even we have all of those difficulties, still the ultimate goal is that we might want to have the GPU running for this combinatorial common filter as well, because the combinatorial common filter is the place that really takes a lot of time compared to just the track fitting. But this comes with much more challenges. One example is that we might want to understand how to parallelize the search of measurements on one surface. And again, this is very limited amount of work for one thread, for one GPU core. But it still takes a lot of time to search this many and many times throughout the detector. And also we have to consider how to handle the branching of the tracks with the combinatorial common filter. I know that the CMS people are doing some work on this. So like very interesting that we can talk with each other to see how this can be done in the future. All right, that's all of my talk. Thank you.
Thank you very much. Are there any questions? Please, if you have a question, go ahead.
But just a comment.
Sorry,
yeah. No, I have just a comment to advertise. if you're interested on this, you should register to the ACTS parallelization mailing list where we announce these meetings. And that's inter experiment, one side R&D line, as Xiaocong said. So be free to join. We don't have regular meetings, we call them on demand.
Yes.
Go ahead, Bowden.
Just two quick questions. One was, I think it was back on slide 7, where you were looking at the speed up versus the GPU. I mean, for the CPU and GPU as a function of number of tracks. What causes the knee? Whoops, sorry, it was slide 8, my bad. What causes that knee at around, what is that, 10, sorry, I need to blow this up so I can see it. Around 50,000. Why does it change there?
You mean we don't see very good speed up if the number of space points is less than 50,000?
Yeah, and there's also a change in the characterization, right? It's it rapidly increases, but
yeah,
then it turns over. Is that a shift from? Then go ahead.
Yeah, I think it's relevant with the GPU throughput. I think we can only see very good speed up if we have enough amount of work to do for the GPU. And otherwise, all of those time is spent on the I/O, and then we can see very good speed up.
Yeah, so that you always have an interplay here. I mean, Charles can I think comment way more precisely. You always have an interplay between data shipping to the GPU, having it busy, and bringing it back. Yeah. Sure,
I agree. And let's see. Let me just make sure this matches your other plot. So for very small numbers, actually, I guess, yeah, the x-axes are the same, right? Number of space points is the same, just the numbers here. But it looks like you have huge amounts of speed up to 50,000 versus the CPU. And then the CPU seems to make back a whole bunch more, you know, at the 100 and 200,000. That doesn't feel consistent with what I'm seeing for the way CUDA behaves, unless there's something that's fundamental in the algorithm.
It is an algorithmic question, Gordon. So this implementation, and again, Charles may be able to say in more detail, but it does run into a limitation on how many threads it can use effectively as it runs. But
sorry, you have to speak up a little bit, Attila. There's some sort of water background noise.
Yeah, I guess much of it is just my laptop being overheated.
Oh.
But yeah, it's mostly an algorithmic question. This is why we are looking at different algorithms for seed finding at the moment.
Sure.
Because the code that this result came from does have a limited amount of parallelization that it can do. And I believe this flattening out that you noticed, this comes from that after a while, even though as input, the code gets more space points and more combinations that it could look at, the implementation cannot take advantage of all of the threads that it may have available.
That totally makes that. I get that, and you know, that plus the transfer time and memory issues perhaps explains that curve. Just what's a little odd is that at lower numbers of space points, the GPU seems insanely faster than the CPU, and at higher numbers of space points, it gets to be around a factor of 2 or so. So something, either the CPU doesn't look to be speeding up. That looks like, to my eye at least, a fairly linear. The blue bar graph that looks pretty linear to me. Okay, maybe down. I'm misinterpreting down in the low part. But whereas the red part.
Scale.
The bar graph is a log scale.
It's a log scale. I should maybe spend a second or more looking. Thank you. All right. Okay,
Also,
that gets the second half of the question.
There's also parts of the algorithm which only execute on the CPU. So you've got, a multitude of different factors which are involved, like the launch latency, the memory transfer back, and then the filtering at the end, which is then on the CPU.
Okay. All right. Perfect. And then I had one other quick question, or maybe not so quick question for Xiaocong, but I see somebody else has their hand up, so I think I'll just put myself at the back of the line.
Thanks, Gordon. Yeah, Dorothea, do you want to go ahead? We don't hear you, but I see you unmuted.
Yeah.
Still, now we hear you, maybe. Oh, no, that's
me.
That's you. Yeah. Sorry, Dorothea, we're still not hearing you. Now we hear you.
Now you hear me? Oh, very good. Sorry about that. So thanks a lot for this nice talk and presenting these studies of ACTS running on GPUs or parts of it. I was wondering for the Kalman filter, for example, whether you had considered actually using any other implementations on GPUs that exist already, because there are also other experiments that are running already Kalman filters on GPU, for example, IRIS, I know is doing that in LHCb. So I was wondering if there had been any thoughts going into actually reusing some of this, or whether there was a particular reason for you to kind of start the implementation from scratch.
So the reason I started with the ACTS computer is because I do some work with the ACTS computer, so it's more easy for me to get started with this. But I said that we'll be very happy to learn how other computer is running on GPU, and also how they achieve the performance gain. So this is exactly something we want to learn.
Okay, yeah, so I think that would be awesome to collaborate in that direction, yes.
Yeah.
And you mentioned that one of the big issues you were, or things that you were studying was the propagation through the different layers. Is it at all possible for the ACTS geometry to go towards a parametrization for the transport? So we've made very good experience in LHCb for that, to parameterize the transport through the material of the detectors and also the magnetic field, for example, based on momentum, PT, track inclination, and variables like that. Is that at all possible? Because that would, I think, speed up quite a bit the, because you don't have as many memory accesses and maybe not as much branching.
So maybe I
can comment on that.
Okay.
if you one of the main clients of ACTS is gonna be Atlas, and the propagation through the Atlas solenoid and the Atlas toroid, which has to be supported, is practically not parametrizable. Since it has particularly the toroid has a vastly changing field to an amount that we actually had to spend time to backport our Runge-Kutta integration into Geant to have the results we want to have. So I think this is a question which cannot be generally asked or answered, let's put it that way, for any detector. It will work fine for several type of setups. But a general solution, I think, for this is more what we are aiming for, trying to get the full numerical integration done, and then you can specialize for dedicated setups.
Okay, yeah, I see that point. Maybe I have one last question, if I may still continue.
Sure, go for it, Dorothea.
Yeah, because if I understood correctly, you were parallelizing across tracks in all these studies. Were there any attempts to also parallelize across events, as you've mentioned that you didn't have enough parallelization to actually load the GPU with work?
I don't think for the moment the parallelization over the events might be more difficult. Yeah, but I think this is the goal of the CKF of the combinatorial common filter because the combinatorial common filter is handling just the one event. So maybe this is something you're talking about.
Okay, yeah. Thank you.
Great, thanks for the questions. Gordon, do you want to go ahead? I don't see any other questions waiting.
It turns out my second question was that question about paralyzing over events. So I'm perfect, thanks. And I agree, that was a fantastic talk. Thanks, thanks for giving it.
Thank you.
Any other questions? Okay, if not, then thank you everyone for coming today, and do stay tuned to see our future IRIS-HEP topical meetings. We have a few planned over the fall. Thanks everyone. Bye.
Bye.
Thank you.